right, in our next section, we're going to talk about the meaning of the secant, the meaning of tangent, and what all this stuff might have to do with an important topic of velocities. Now, we've heard the word secant, we've heard the word tangent. Normally, we've heard those in association with trigonometry. Now, in calc, in addition to the trigonometry application of secant and tangent, secant is also thought of as a line that intersects a function at 2 points. So, if I have a function that looks like this, and I draw a line like this, that would be considered secant line because that line intersects this function at 2 different points. So that's known as a secant line. And if we find the slope of a secant line, the slope of the secant line, the slope between this point, we're going to take y2 minus y1 over x2 minus x1, that becomes the average rate of change of this function. So between here, the function is changing, all the way until we get to there. If we want to find the average rate at which this is changing, we find the slope of that secant line. Now, tangent is also a line. And it intersects a function. But a tangent line will intersect the function at only 1 point. So if we have a similar looking function here, and we want to draw a tangent line, maybe we draw a line that looks like this. And that line just barely skims this function, hits at that 1 point. Now, if we can find the slope of that line, we're going to talk about how to do that. But instead of giving us an average rate of change over a particular interval, what this is going to do is it's going to give us the rate at which this green function is changing at that particular instant in time. So that is an instantaneous rate of change. And I should not have written over a certain interval. It should just be an instantaneous rate of change at that moment. Now what velocity is a very specific rate of change. Velocity is found, and for those of you who have taken physics, who are in physics, this is going to be something that's going to be pretty key to your understanding of velocity in physics. Velocity is found by calculating the slope of a position time graph. So if we have a function here, we've got the position, here we've got time, and we've got some kind of a position time graph, if we find the slope at any particular instant, or if we find a slope of a secant line over a particular interval, we are finding either the instantaneous velocity, if we're finding the slope of the tangent, or we're finding the average velocity over an interval if we find the slope of a secant. But that's going to be our understanding of velocity. It's the slope of a position time graph. Now, we want to find the equation of a tangent line. It's going to be a really important skill. It's going to be pretty much emphasized on the AP exam. How do you find the equation of a tangent line? There's going to be a number of different ways. We're going to show one way. And here we've got a function y equals x squared. We've got the point 1, 1, and we want to find the equation of the tangent line. And if I were to just kind of highlight which one that is, well, I don't know, I kind of think it's this one. So I want to find the equation of that line. And to find the equation of a line, well, we've got to have the slope times x plus some y-intercept. All right, now, what I'm going to do is I'm going to make a little table here. And I've got x values here and here. And we've got y values. And the y values, remember, f of x or y is equal to x squared. So all I've done is taken these x values and squared them. So why don't you go ahead and press pause and fill in these y values. Save a little time. Fill in those y values by pressing pause. Okay, you're back. Now, I want to find the slope of that red tangent line that I've drawn. And so what I'm going to do is I'm going to find the slope between here and here. The slope between 0, 0 and this point 1, 1. Okay, I know 1, 1 is on the tangent line. Well, if I find that slope by taking y2 minus y1 divided by x2 minus x1, I find the slope is 1. Well, now if I move over to 0.25, that would be right here. My tangent line would be something like that. Not quite the red line, getting closer to it, because neither of these green segments that I've drawn really look like they would represent that tangent line. But I'm again going to find the slope between this point and this point 1, 1. So I take y2 minus y1. I divide by x2 minus x1. If I do that, I get 1.5. So what I'd again like you to do is press pause and find the slope between each one of these points and the point 1, 1. y2 minus y1 over x2 minus x1. Do that for every single one of these ordered pairs that we have that are on the function y equals x squared. And then come back and we'll talk further. All right, these are the slopes that you should have found. And as I'm thinking about this graph and trying to come up with the equation of the tangent line, and I'm just going to give myself a clean slate here. I think that if I want to find the accurate slope of this tangent line, instead of choosing a point that's pretty far away from 1, 1, I think what I want to do is I want to pick a point that's really close to 1, 1. And I think that this slope pretty much represents the slope of this entire tangent line. So I want to choose points that are very, very close to 1, 1. Now, let's take a look at our table. I think this point is pretty darn close to the point 1, 1. And what's the slope that we found between that point and 1, 1? I think this point is really close to the point 1, 1, just ever so slightly after the point 1, 1 on that function. Look what that slope is. So if this gives you the best picture of what the slope of that tangent line is going to be, what do you suppose by looking at these two numbers, slope of that tangent line is going to be? Well, if you're saying you think the slope is probably going to be 2, I think you're right. Because we chose points where we found the slope of the secant, a very small secant segment, very, very close to the point of tangency. That gives us the best estimate for the slope of the tangent. Now, if we got to find the y-intercept, all we have to do is take our partial equation that we have here, because we're missing the y-intercept. We have to plug in a point. Well, I do know the point 1, 1 is on the tangent line. So I'll put a 1 in for y. I'll put a 1 in for x. And I'll figure out what the y-intercept has got to be. And if I find that correctly, I do believe that we should find the y-intercept to be a -1. And as we look at the actual picture here, yeah, pretty believable that that would be -1. So this is one method that we have of finding the equation of a tangent line. We'll have more as the year goes on. But for right now, I'm hoping that this method makes sense by finding the slope using secant segments that are very, very close to the point of tangency. Now, here we've got another example. Suppose the data in the margin comes from some experiment. Y is a function of x. Use the data to draw a graph of the function and estimate the slope of the tangent at the point x equals 0.2. Well, now you're going to press pause, and you are going to, I've put a scale on here so you can use this exact same scale. And I want you to plot those points and then draw a curve that goes through those points. And then once you've done that, then come on back to this discussion. All right, so we've plotted these points. We've drawn a curve that fits as best we can. Now I'm going to draw a tangent line at x is 0.2. So right here, I'm going to try and draw a tangent line. See what I can do here. I'm going to make a couple of adjustments in that. You know, that looks pretty good. And then what I could do, because my task here is to estimate the slope of that tangent line. Well, okay, I could try to figure out, well, what point is this up here that it would hit? What point is this down here? And I could guesstimate at those things. But the way our author, James Stewart, furthermore known as James, what James wants us to do to estimate the slope of that tangent line is just to use the points closest to 0.2. Let's find the slope between these two guys as close to 0.2 as we can get. So let's take y2 minus y1. 3.02 minus 3.71. y2 minus y1 over x2 minus x1. And if we do that correctly, I think we're going to get negative 0.69 over 0.2. If I divide that out correctly, I believe I get negative 0.345. So if we're given a table of values and we're asked to find, or estimate, not find, but estimate the slope of the tangent at 0.2, we find the slope using the points closest to 0.2 on either side. That's going to give us the best estimate. If I actually drew the slope between those 2 points, kind of looks parallel to what I've drawn before, doesn't it? And therefore, yes, those would have very, very similar slopes to each other. All right, final slide. We are going to try to find a velocity here. Velocity, and this isn't a good word here. Let's call this velocity at 5 seconds. That's an instantaneous rate of change. That is the slope of a tangent. And you know what? Just to be really clear here, we're not going to find that velocity. We're going to estimate that velocity. Let's estimate the velocity at 5 seconds. Now we do have a height function here. And the height of this object that's being dropped will be found by plugging into this negative 4.9 t squared, where t stands for time, plus 450. And so if we're going to estimate this, what we're going to do is we're going to use a secant that is really close to the 5 second mark. And so what I'd like to do is this, and you're going to shortly press pause, but I want you to use a time of 4.99. And then I want you to find the height of this ball that's being dropped. And let's see, we want a secant, so we're going to use something just the other side of 5. And let's find that height. Let's find those numbers as accurately as we can. And then we'll come back and we'll figure out the slope. So press pause and find those numbers. In each case, we got something pretty darn close to 327. Now, if I'm going to find the slope of this secant, which is really, really close to our point in question here, that's going to give us a good estimate of the slope of the tangent. So I'll take y2 minus y1. If I do that correctly, I believe I get negative 0.98 divided by x2 minus x1, or actually t2 minus t1, 0.02. And I get negative 49. Now in this case, we have units. These numbers right here, these 327s, those are measured in meters. Those are a height. So this was in meters. And the units for these values, very close to 5, time is measured in seconds. So when I did this division, I was taking meters and divided by seconds, giving us meters per second. And is it any surprise that this velocity would be negative? Well, anything that's traveling downward, the velocity would be considered negative. Traveling upward would be considered positive. So no surprise that we would get a negative velocity. So, hopefully that gives you a better understanding of the term velocity, what that means in calculus, and how to find an average velocity, or by making really small secant intervals, finding an instantaneous velocity.